Let's take a look at how you would run a regression analysis from start to finish. I'm going to use as a data set 20 paired observations or measurements xi, yi's of various hydrocarbon levels, that's the x variable, in pure oxygen levels, that's the y variable, in various samples of fuels. So you can get the actual data set from the accompanying notebook. And the first thing we'll do is to try to describe the relationship between x and y. We can describe the strength of association with the help of the coefficient of correlation, rho. Before we do so, let's take a look at the data. What I'm seeing here is that there is a relationship between the x values and the y values. When x increases, it looks as though y is also increasing. When x is decreasing, in general, the y value is decreasing. You compute the correlation coefficient. In R, you do so using the COR function. Be careful, there's a function called COV, the covariance, which measures something that is somewhat related to the correlation, but it is not the same thing. You get a value of about 93.7%. Now you can compute the coefficient of correlation directly by computing the following quantities. We have SXY, which is the sum of all the products, values of x minus their mean, values of y minus their mean. We have SXX, which would be the sum of the square of the differences between the values of x and the mean of x. SYY would be the sum of the square of the differences between the values of y and the mean. And out of this, we can build a correlation coefficient rho. It is going to be SXY divided by the square root of the product of SXX and SYY. And sure enough, we get the same value, about 93.67%. It's a pretty strong correlation, and that's aligned with the observation that the points seem to be increasing in height when they increase in horizontal distance, and vice versa. The other thing you can say is it looks as though there's a bit of a line, that the points are scattered around that line which is hidden. That is supported by the information that the coefficient of correlation is very strong. Now, how do we find this line of best fit? R is primarily a tool for statistical analysis, and so it has a lot of built-in functionality to do regression analysis. We'll start by building a data frame with the variables. We'll combine x and y together into a fuels object. You see that it contains 20 observations with measurements of x and y arranged in columns. That's the format we need to be able to use the function LM, linear model, in R. And we'll regress y against x using the fuels dataset. We'll put all this into an object called model. This is what the model summary actually looks like. I have some information about the residuals, which we know are supposed to follow a normal distribution with mean 0 and with variance sigma squared. And the residuals are actually we would expect their median to be around 0, and the first quartile and third quartile to be somewhat symmetrical, and the max and min to be somewhat symmetrical as well. Then we also get some information about the estimate of the coefficients. If we think that this is meant to be a straight line, then this quantity here tells us what the intercept of the straight line will be, and this second estimate here will give us information about the slope of the straight line. It looks as though a straight line takes on this equation, 74.3 plus 14.9 times x. Let's plot the line of best fit. I'm going to use a slightly more professional looking plotting functionality, and we'll do it with the Ggplot library. If you haven't installed Ggplot 2, you need to first install it. Once this is done, it's going to take the object model that we've created, and it's going to create a plot out of that. It's going to first plot the points, the x and y's, then it will add a line using the fitted values of that one. If you wanted to add the residuals, remember the residuals, these quantities here, you can modify the call just a little bit. It stays roughly speaking the same, but now we will add a new object called line range. Line segments which will be colored in red, which goes between the actual y value and the fitted value. So the true y value and what we predicted based on the line of regression. It's something that looks like this. Now, what is the estimated variance of these residuals? If this is a good fit, the residual should follow, as I said, the normal distribution between 0 and variance sigma squared. Well, what's the sigma squared likely to be? We can estimate it using the mean squared error, which is the sum of squared errors divided by degrees of freedom n minus 2. We've given you a formula for that. You can find it in the notebook. SYY minus V1, the point estimate for the slope, times SXY divided by n minus 2. Let's actually compute it. We need the value of n. We know it's 20, but let's set it up this way so that if you had a different data frame, you'd also be able to compute it directly. And then I'm just going to implement the formula that I've given you here. How do I get B1, my value for the slope of the line? I know it's about 14.9, but how do I get the real value? You can extract it from the model. So model is an object in R. It has attributes. Look at the coefficients attribute of model. You will see this is an array with two numerical quantities. You're interested in the second one. Sure enough, 14.47. This is where you would find the value B. So our estimate for the variance is about 1.18. You can also extract that information from the model summary. Even though it didn't display in the output of the model summary, it has been computed by the routine LM. Now, the first place you would look for this estimated sigma would be through the list of the attributes of the model itself. If you look at the attributes, well, it has the coefficients. This is how we extracted B1. It has the residuals, the effects, the rank, the fitted values, the assign, the QR, the F. I'm not seeing the thing that I want. It turns out that sigma is not an attribute of the model. It's an attribute of the summary of the model, which is itself its own object. You'll see it here. Sigma is the first, second, third, fourth, fifth, sixth attribute of the summary of the model. So if you want to get the mean squared error, sigma squared, you can literally extract it from the summary of the model, get the sigma quantity, and then you square it, because then C is the square of this sigma. And we get 1.18, which is exactly the value that we computed previously. So now you might be interested in testing some of these statistics. Let me output the summary of the model again. We have an estimate for the intercept, an estimate for the slope, 74.28, 14.95. Based on the data that we've observed, we've computed these estimates, and we can run various tests. If we wanted to test, for instance, whether the intercept was really equal to 75, or if it could be potentially smaller than 75, then we would run a t-test. So let me extract the coefficients B0 and B1, my point estimates. They come from the model themselves. I'm giving them these numbers just to double check here. B0 is indeed 74.28. P1 is indeed 14.9. Okay, so we have the numerical values for the point estimates. So we compute the corresponding t-statistic. If the null hypothesis is true, if it turns out that the true value of the intercept is 75, then B0 minus 75 divided by the square root of sigma squared times the sum of all of the square of the components divided by n divided by SXX would follow a student t distribution with n minus 2 degrees of freedom. So let's compute this t0 statistic. Takes on the value minus 0.44. The question we have now, is it likely that we would observe such a value if we draw from a student t distribution with n minus 2 degrees of freedom? That does not look like an extreme value. We need to compare it to some critical value of the same t distribution, 5% confidence level, with n minus 2 degrees of freedom. What is this value? Minus 1.73. So it definitely looks as though the t-statistic is not within the critical region. The region here where the area is 5%, and the rest of the area underneath is 95%. So we don't have enough evidence here to reject the null hypothesis that the intercept is equal to 75. And that makes sense, right? We look at the data and it looks like the intercept could be 75. So we can't reject the null hypothesis. But remember, we never accept the null hypothesis. We can also test for the slope being equal to 10. Our point estimate for the slope is 14, which is starting to be a little bit far from 10, relatively speaking. So if we wanted to test for the null hypothesis that it is equal to 10 versus the hypothesis that it should be greater than 10, we think it's greater than 10. Our estimate is 14.5. We would hope that the test would show that it is indeed greater than 10, but we have to verify if the data supports that. The test statistic for the slope is a bit different. Under the null hypothesis that the slope is really 10, then the quotient, point estimate B1 minus our candidate divided by the square root of sigma 2 divided by SXX. That should follow a student t distribution with 18 degrees of freedom. We compute the critical value for that student t distribution with 18 degrees of freedom at the 5% level. This time we're in the upper end of the spectrum because we're testing for the alternative that the true slope is greater than candidate 10. And you will find that it is indeed in the critical region. The test statistic is 3.75, fairly high, given that the critical value is 1.73. So we are fully in the critical region at the 5% confidence level, and so we would reject the null hypothesis that says that the slope is equal to 10 in favor of the alternative, in this case, that the slope is greater than 10. The data seem to suggest this would be the case. And if we wanted to test for significance, test whether beta 1, the slope, is equal to 0 or different from 0, it's the same test as the test for the previous one, except here our beta 10 candidate, the value that we're testing against is 0. I want to know if it's a flat line or not. It doesn't look like it should be a flat line, but who knows? Let's see what the data says. So we compute the t statistic for significance under the null hypothesis that the true coefficient for the slope is indeed 0. We get a value of, well, this is a huge value. What is the probability that we would observe this value by chance in the t distribution with 18 degrees of freedom? That probability is going to be slim. Sure enough, because this is a two-sided test here, we're testing against the slope being equal to 0, so in either direction. The critical value requires you to look at the 2.5% confidence level. If you want an overall confidence level of 5%, compute the critical value here, just explicitly write it down. It's much smaller than the t statistic. And so in absolute value, is the t statistic greater than the critical value? Yes, it definitely is. Sum of both of these together, this is 95%. What we're saying is that this critical value here, this point, will be 2.0, roughly speaking. And we have found a t statistic, which is way into the critical region. So the regression is quite likely to be significant. The last thing I want to talk about is where you can extract the F statistic and the R-squared statistic from the actual model summary for the linear regression. It is provided by the actual output. The F statistic value, 128.9, and it tells you the number of degrees of freedom that you get here, 1 and 18. Together with the p-value, the probability that the F distribution with 1 and 18 degrees of freedom would give you values greater than 128.9. And you see that this p-value is abysmally small. Right? This F statistic is actually quite significant, which means that we truly believe that the regression is significant. And you can also extract the coefficient of determination, what percentage of the variation is explained by the linear regression itself. It is 88%.